Well, yeah, so today I'm going to be doing a survey of recent methods in prompt optimization and parameter-efficient fine-tuning. I want to start by acknowledging some of the collaborators at the Vector Institute and elsewhere on this work that we are doing at Vector. So Faiza, Saeed, Jacob, and Akshita, we've all worked closely on this, this talk and the methods that we're researching at Vector. So just to level set on some vocabulary around prompting and what I'm talking about today, we'll start by introducing some of the concepts like zero shot. So prompting in general, you're all probably fairly familiar with it. Zero shot refers to situations where you have maybe an instruction that you've given to your language model, but you haven't given it any training examples specifically as part of the input to the language model. One shot is where you give it one example along with the desired completion or task that you're trying to actually perform. And then few shot refers to adding at least more than one example to your input in order to guide the language model to perform the task that you're trying to do. This is often referred to as demonstration learning, few shot prompting, in-context learning, or prompt augmentation. It's a very wide vocabulary around this very simple concept. And this becomes increasingly effective as the model size grows. So I'm going to go through two slides here to motivate why we want to talk about prompt optimization and parameter-efficient fine-tuning. So language models are general task performers. They can perform certain tasks with state-of-the-art accuracy. So the Lambda task is essentially a completion task. And it can actually do a really good job at that, surpassing at the time when GPT-3 was released, the state-of-the-art model for that task. However, you can see on the upper graphs here that for certain tasks, like the superglue task, which a lot of people care about, language models alone, even with in-context learning, have a pretty large gap to state-of-the-art fine-tuned models. So it surpasses fine-tuned BERT, but a state-of-the-art model can do that set of tasks way better than a language model, even when it's prompted with examples. The second example here is that how you ask the model to do the task really matters, even when you're fine-tuning that model while asking. And so this is an example of a bunch of different ways that you might be able to prompt a model, in this case the BART model, to perform a named entity recognition task and the various levels of accuracy, or excuse me, F1 score that the model achieves using those prompt templates along with fine-tuning even. And so you get a very large fluctuation in the model's performance depending on how you ask it to do the task that you hope that it's going to do. And so this motivates automatic methods to optimize the prompts that you're giving a language model. And so there are two main categories in this, discrete and continuous prompt optimization. In the discrete setting, the prompts are and remain readable and possibly interpretable, though I'm going to give you an example as to a situation where that's violated very significantly. Often, though the approach we're going to talk about today actually requires model access, other methods don't necessarily require model access to do this type of optimization, which is a nice approach if you're using open APIs or something like that. The second category is continuous optimization, where we leave natural language prompting behind, and we actually perform optimization in some embedding space of the model itself. This leads to pretty impressive downstream performance, but it usually requires weight updates or some sort of training, and so if you don't have access to the underlying model, maybe this approach isn't for you. And then the final is that interpretability of the prompts that you are optimizing is fairly complicated, and there's some really nice work around showing that it is very difficult to interpret the prompts you get with this method. So we'll start with an example of discrete optimization. I'll just give one that motivates some of the continuous optimization approaches, but there are a lot of others that you can investigate. So we're going to start with gradient-based search. This is called auto-prompt, not to be confused with some of the other auto-prompt methods that have come out. But the idea with auto-prompt is that you have some, say, text that you're going to input into the model, and then you're going to be optimizing some trigger tokens that will help the model perform the downstream task. In this particular approach, they used a masked language model specifically Roberta, to sort of fill in that mask token with the response that the model is supposed to give. And so I'll harken back to some of the multivariable calculus that you might have had in the past, and remind you that the directional derivative for a scalar function is obtained by taking the direction that you want to compute the derivative in and dot producting that with the actual vanilla derivative of the function that you care about. Why am I mentioning that? Well, this is the way that autoprompt actually searches for optimal prompts by manipulating the tokens using a directional derivative. So the idea is that you select a random token, the ith prompt token, and it has some sort of embedding associated with it with the model, and you search for other tokens that you might want to replace that token with, and the way you do that is by computing the directional derivative with respect to the embedding of the tokens, the token candidates, and you select the top k token candidates that improve the log probability of the label given the prompt that you already have. And so that's a direction that you might want to step to improve the model's ability to complete the task that you want it to do. And so the way they do this and evaluate it is they take a double batch approach. So you have a bunch of training examples, you select 2 batches instead of 1. The first batch allows you to compute those top k candidates with the directional derivatives associated with that batch. And then the second batch is used to score those candidates, and you take the candidate that provides the best performance on the batch that you've selected in the second round. If there's no improvement, maybe your derivatives sort of led you astray, then you retain the prompt that you originally had without the modification of any of the tokens that you've identified as candidates, and you move into another set of double batch selection, and you try and improve from there. So does this work? It's sort of an interesting and very cool idea for me as a mathematician. The answer is yes. So on the top here, there's sort of various ways of fine-tuning a model with a BERT and Roberta model. And on the bottom here, you have performance for BERT and Roberta with a manual prompt, meaning someone designed that prompt to try and get BERT or Roberta to perform the task that it cares about. And you can see that there's a large improvement using autoprompt over the manual prompt design for BERT. In the case of Roberta, you don't get to fine-tuned performance, but you do surpass something like linear probing, and you get a really sort of competitive performance. And this type of thing improves as you move up in terms of model size. So let's revisit the interpretability comment that I made earlier. So this is a model and an approach that we've been experimenting with at Vector. For SST2 and semi-val, you can see the top line is a human engineered and sensical prompt that you might ask T5 large to do a sentiment analysis task. And so you get okay performance, better than random, but it's not great. If you use autoprompt, you can see on the right-hand side a really large increase in accuracy, but on the left-hand side, you can see a really crazy prompt. It's kind of insane that this prompt actually improves accuracy over the natural language text, but it does, which is really sort of interesting and also odd. This method needs gradients with respect to the model. You also need to take dot products over the vocabulary, as I talked about. And the method can sometimes have convergence issues because you're doing a first-order approximation in your token manipulation. Other methods don't need these types of things, so grips or RL prompts can do this and are very competitive with autoprompt, with data efficiency and that sort of thing, without needing model access. So those are really interesting. But the reason I talk about autoprompt specifically here is it motivates some of the continuous optimization approaches that are very popular and yielding state-of-the-art results. So there's a continuous family of prompt tuning approaches. Those are prompt tuning, prefix tuning, and P tuning. Prefix tuning and P tuning are actually the same approach, but with slightly different modeling choices. But the idea is that we leave natural language prompting behind. The model already embeds our natural language prompts into a high-dimensional space, so why not optimize our prompts in that space instead of in the natural language space? Prompt tuning falls into a broader category of parameter-efficient fine-tuning. We're going to talk about 2 methods in that to end our talk that sort of leave prompting behind and move towards strictly parameter-efficient fine-tuning. The first and sort of simplest idea is prompt tuning. It's a straightforward relaxation of, say, the discrete prompt optimization. You have a separate reserved prompt embedding matrix. You, instead of having natural language tokens, you have a set of virtual tokens associated with prompts. And your entire language model is frozen. You only compute gradients with respect to the prompt embeddings, this new embedding matrix that you've constructed, and the rest of the sort of components of the model flow through naturally. You don't update anything, and you optimize performance strictly through the prompt embeddings. So how does this work? So some of these training trajectories are a little difficult to see, but hopefully I can get the point across. For T5 large, again, some internal experiments that we've done. The two main lines that you want to see here are the blue lines and the orange dashed lines. So the blue line is prompt tuning, using on the left 50 prompt tokens, on the right 100 prompt tokens. And you can see that that blue line is very competitive. In the case of SST2, it actually surpasses model fine-tuning, even for T5 large, which isn't a massive model, but it is a fairly large one. And you can see the reduction in parameters that you have to tune, 770 million versus 50,000 if you use 50 tokens, which is a huge speed up in terms of efficiency, especially to get competitive performance. For some other tasks, so for the superglue task, this is from the original prompt tuning paper, you always outperform in-context learning or prompted GPT 175. This is for T5 11 billion, and so it's an order of magnitude smaller than GPT 3 175. And with scale, as T5 gets larger, your prompt tuning approach, the green line, actually catches up to and surpasses model fine-tuning. And so why not use the really efficient approach rather than fine-tuning these big models? There are additional advantages to prompt tuning and to many of the parameter efficient fine-tuning methods that I'm going to talk about. The first is mixed batch tasks. So in order to get a model, an underlying model, to perform different tasks in this approach, all you have to do is couple your input with the embeddings that you've trained associated with the task involved, and then everything flows through the model itself. And so you can actually stack these embedding inputs into mixed batches for mixed tasks. And you can just sort of throw them all through the model all together, and the model will perform different tasks just by virtue of the calculations that it's doing, which is really, really efficient and effective, allows for reuse of the model rather than, say, fine-tuning 11 different models for 11 different tasks. There's also evidence of domain adaptation advantages, so you're leaving the underlying model intact for most of these methods, and so you let it be sort of a general model with some guidance associated with the parameters that you're injecting. And so you can see the model column here on the in the table is fine-tuning the model and then trying to move it to a different task versus prompt tuning the model and trying to move it to a different task. And you can see that in 4 out of 6 of these sort of different domain transfers that the prompt tuning approach actually outperforms model fine-tuning and then changing to a different domain. So prefix tuning, and as I said, p-tuning, which is a very similar approach, just different modeling choices, actually generalizes this approach a bit further. And instead of just having a single layer of prompt embeddings that you're training, you have a stack. And there's essentially a prompt embedding for every layer of your transformer model. The way they parameterize these embeddings is through an embedding matrix similar to what we had for our prompt tuning method. And then they apply a dense neural network to sort of flesh out or flare out the dimensionality a little bit to match the sort of stacked dimensions of your transformer. And so these HIs are injected into your transformer at each level rather than just at the beginning, as you would see in prompt tuning. So how do you actually get them into your transformer model? You actually inject these into your attention mechanism. And so at each layer J, you actually split that HI value into 2 components, one associated with the key values of your transformer, one with the values, excuse me for the double word there, but the idea is that you inject those into your keys and values, and that allows you to manipulate the attention mechanism very efficiently. And so there's a concatenation of the embedded token pieces along with your K and V values that pass through the transformer itself. And so these are actually results from p-tuning. As I said, they're very similar, similar ideas, just slightly different modeling choices, but the results are a little bit better, in my opinion, in terms of presentation. You can see on the left, the blue bar is just prompt tuning alone for smaller models on the left and larger models on the right. And so as I said, as scale increases, you can recapture fine tuning with prompt tuning. But p-tuning, because you're injecting at every layer, allows you to actually capture fine tuning performance earlier in terms of the model size than you would with p-tuning. And so you can see on the sort of superglue task on the right, p-tuning is extremely competitive, even for small models with fine tuning alone. And it's still extremely efficient because you're only manipulating a small number of parameters compared to the overall model. All right, so now we're going to leave prompting behind as we left discrete prompting behind earlier in the talk. And we're going to talk about purely parameter-efficient fine-tuning approaches. So you might have heard of LoRA. It's fairly famous now. It generalizes the idea of language model adaptation past prompting and actually adds in a reparameterization of each of the layers, but it still focuses on manipulating the attention of the transformer. The idea is based on the empirical observation that transformer weights throughout the model are of what we would term intrinsic low rank, or intrinsically low rank, meaning that if you did an eigen decomposition, you'd only have a certain set of the eigenvalues that are really large. The rest of them sort of fall off a cliff. This was originally proposed for natural language, but it's been applied to other models, for instance, in vision, extremely effectively. And so what's the basic premise? It's sort of a simple idea. If the weight matrices associated with your transformer are of intrinsic low rank, maybe the fine-tuning updates also are. And if that's true, then you can represent them by low-rank decompositions. In this case, they're represented by B and A. And so through training, LoRA constrains the weight updates to be represented by these two low-rank matrices, B and A, where R is that low-rank representation. So R can be very, very small for LoRA. We'll look at some experiments with that in a second. But the idea is that if the fine-tuning updates are also low-rank, B and A will capture them extremely accurately. And so what weight matrices should you actually decompose in this way and update with LoRA? So this is a couple of different choices associated with a multi-headed attention mechanism. So you have weights associated with the query, key, and value pairs, or excuse me, triples. And then you have an output sort of projection matrix that you might also use LoRA for. You can see R in this case is very small. So R at the largest is 8. It goes all the way down to 2. For some of the experiments, they saw that R equal to 1 was sufficient, which is essentially an outer product of two vectors representing your matrix updates, which is really efficient and small. What they found through this experimentation was that, again, manipulating, in this case, Q and V attention mechanisms were sort of the most efficient approaches, which actually mirrors what prompt tuning and p-tuning sort of found as well, right? In p-tuning, we manipulated the K and V values. That's sort of equivalent to manipulating the Q and V values here, which is really interesting. And so how does it perform? So for GPT-3, 175 billion parameters, LoRA at the bottom there, when R is equal to 1, you're only updating 4.7 million parameters. So at least 2 orders of magnitude better in terms of efficiency. If you move up to a rank, I think, of 8, while tuning the Q and V values specifically, you get around 40 million parameters. Still extremely small. And LoRA, in this case, outperforms by quite a fair margin in certain scenarios fine-tuning of GPT-3 and some of the other methods that we talked about. So pre-embed and pre-layer are the prompt tuning and prompt and p-tuning approaches that we already talked about. An adapter is another sort of efficient fine-tuning method. So there are situations where parameter-efficient fine-tuning methods or these prompt tuning methods might be insufficient. And so one of them is in the sort of data poor setting where you only have a couple of training examples. And so IA3, which stands for Infused Adapter by Inhibiting and Amplifying Interactivations. I'm going to stick with saying IA3. is an approach that modifies the attention mechanism again, but also contemplates modifying the feed-forward mechanism. In this case, all they're doing is they're taking these LV, LK, and LFF vectors, and they're taking a Hadamard product, so just an element-wise dot product to each of the vectors associated with the tokens, flowing through your attention mechanism, and also a vector to manipulate the token embeddings associated with your feed-forward layer that happens after attention. This is really efficient because these are only a single vector. There's not like a stack of them or a matrix of them. And they work off of T0, which is a small model based on T5 that is specifically tuned for zero-shot predictions and does a really good job, even on its own without parameter-efficient fine-tuning. The focus, as I said, is on situations where you have much less than 100 labeled examples, ranging from 20 to 70 in their paper. And there's a bunch of different tasks averaged into the figure on the left there. But you can see that IA3 is that yellow star at the top. It's the only one that performs better than parameter-efficient fine-tuning in this low data regime, and consistently does so across all of the tasks. There's also some really impressive results on RAFT, which is a low data data set with 15 different tasks where you only have 50 examples to train on, and they're all sort of various different tasks in NLP that are specific to applied and downstream use cases. You can see here in this low data regime, these are the top 5 as the writing of IA3 performing models on, I guess, if you call a human baseline a model, on the RAFT data set itself. TFU, which is the IA3 regime or approach, is far and away the best model on this setting. But you can see GPT-3, because it's a very general and good in-context learner, actually is one of the top 5 approaches for this particular data set because of its sort of adaptability with a very small number of examples. Great, so just some end notes associated with IA3, personal questions for me, as it's a fairly new method. Does IA3 maintain its margin with increasing training data? They don't talk about that in the original paper. Is it effective in loaded data regimes where you're not sort of cheating a little bit by having an underlying model that's already good at zero-shot predictions? Also, as noted by the authors, prompt tuning actually appears to be pretty poor for this particular task. Even though there is evidence that it can be effective in low data regimes. They don't really address why. They posit maybe it's the underlying model, but it's not a particularly satisfying answer. And then finally, personally interesting, there were no ablation studies with respect to the vectors that they chose to use in IA3, LV, LK, and L feed forward. Does adding LQ make a difference? Does dropping the feed forward adaptation layer make a difference? There wasn't a lot of discussion on that, and I'd be curious to see if the feed-forward mechanism is really that important to the actual performance of the model, or the approach, excuse me. Great, so that's it for me. I hope I left enough time for questions. I was hoping to, and happy to take any that you might have. Oh, I forgot the timer's down there.
Thank you, David, for that amazing talk. Yes, we have time to take questions. One question? One question up front? Yeah, microphone's coming. Yeah.
Thanks. I just had a question about slide 13. I don't know if you can go back.
Sure, yeah, I can.
Yeah, this one.
This one? Yes, okay, 12.
I was wondering, what is the explainability of how auto-prompt comes to these more effective prompts? Is this still a black box, or is this showcasing something intrinsic about the black box language models that we're testing on? Like, how do we get these?
Yeah, that's a great question. So auto-prompt is essentially a first-order manipulation of individual tokens, right? It doesn't have a necessarily holistic view of the prompt, and so One, it doesn't have a lot of idea of coherence, right? So if you're just moving one token at a time, you're very quickly going to move to something that a human doesn't really read naturally. One of the sort of thoughts that I have around this, and auto prompts and a lot of these methods don't really address, how do we get into these weird prompts that work well, is that you're trying to optimize something in a very discrete setting, and so you're sort of constrained in the directions that you can go. Because you need to stay in the natural language space, whereas prompt optimization is sort of doing a much more granular, continuous approach. And so some of the thoughts around this might be that the space that's optimal for the model in the continuous space is not necessarily achievable in the natural language space, but we might actually be sort of getting close to it in the discrete space, right? Because we can only take specific steps around that. And so we might be sort of converging to that point in space, but when you actually map it back to natural language, it's not particularly sensical. There's a hypothesis, but again, it's not particularly well studied yet as to why we get here. And as I said, the discrete interpretations of continuous prompts is also very complex. That prompt waywardness paper is quite interesting. It shows that you can effectively create nonsensical prompts that perform well around the prompt optimized space that you found, and it sort of doesn't hurt you too much in terms of performance. So it's a good question, not one that I have a great answer to.
Thank you again for the great talk, and I have a question that's maybe a bit elementary. So the first time I came across something called prompting was obviously with ChatGPT, but this is not the prompting of ChatGPT. This is more technical, more within the embeddings. And so when you are prompting the BART and BERT models, the prompts themselves are first embedded, and then they're fed into the BERT models, or if you don't mind explaining the process of it.
Yeah, sure. So maybe I'll go to the diagram I have here. So a language model, specifically in this case a decoder model or a generative model, which is what ChatGPT or any of the GPTs are based on, has sort of an initial layer where you take your language tokens. So you can see on the right there, there are a bunch of language tokens that you might inject into the model. Those are mapped to a continuous space. So you might think of it as mapping the word here, great, to a 100-dimensional vector. Those 100-dimensional vectors are then what flow through the transformer itself and are manipulated through the attention mechanism and those feed-forward mechanisms. And so similarly, BERT has a text embedding layer that it works through, and most of them will. And so that allows you to map your language space into a continuous space right off the bat.
Thank you.